So we're on section 3.3, and this is a super important section to get good at. It's trigonometric identities, and it's not that they're so much useful in and of themselves as that you'll be working on a lot of techniques that will help you in the next section we do about solving equations. So the objectives in this section are just to use algebra. So we're going to be working on the algebra of trigonometric functions. So use algebra to simplify. So first we're just going to simplify trig expressions. So notice you don't solve expressions, you just simplify them. And then we're going to establish identities. And this is the same thing as the instructions verify, prove, all those really mean the same thing to show that it's true. So recall that two functions are said to be identically equal if f of x equals g of x for every value of x for which both functions are defined. So such an equation is referred to as an identity. And an equation that is not an identity is called a conditional equation. And the reason this is important is so you know which are you trying to do. Verify an identity or show that it's always true for every value of x, or the conditional equation is where we're trying to find a value or values of x that will make the equation true. So here's an example of an identity from algebra, and we have 3 times the quantity x plus 2 equals 2x minus 7 plus x plus 13. So if we simplify, we'll get 3x plus 6, and then combine like terms, we get 3x plus 6, so that if you subtract 3x from both sides, you get 6 equals 6. Subtract 6 from both sides, you get 0 equals 0. So hopefully you've run into this before, and if you get 0 equals 0 when you simplify as much as you can, no matter what value of x you choose, this statement will be true. So in algebra, we would say that the solution set is all real numbers, because we were trying to solve for numbers. So when you got this result that makes sense, 0 is equal to 0, you would say this equation is true for all real numbers. So the solution set is all real numbers. Okay, so another identity is x squared minus 1 equals x minus 1 times x plus 1, because any value of x will make it true. So we have learned some trigonometric identities that will continue to come in handy. So sine squared x plus cosine squared x equals 1. This is true for any value of x. Or you can say for every value of x, whichever way makes more sense to your brain. We've learned that the tangent of theta equals the sine of theta over the cosine of theta. And this can be thought of as either a definition, so we learned it as a definition, but it's also an identity. It's true for any value of theta. So here's some examples of conditional equations, so you see the difference. So suppose we have 2x minus 1 equals 0. There is only one value of x for which this equation is true, right? I have 2x minus 1 equals 0. I add 1 to both sides. I divide both sides by 2 and get x equals 1/2. This is the one and only value of x that makes this equation true. So the solution set is the single value 1/2. That is the only value of x that makes that equation true. So you can solve conditional equations, but we don't solve identities. But we can use identities later to help us solve equations. So that's the reason so many of them have been developed, and learning to prove them helps you develop your algebra skills with trig functions. So here's a bunch of the identities we've learned so far. The quotient identities, reciprocal, Pythagorean identities, all their various forms. So remember that if we have sine squared of theta plus cosine squared of theta equals 1, then it must also be true that 1 minus sine squared of theta equals cosine squared of theta. And 1 minus cosine squared of theta must also equal sine squared of theta. That these can all be rearranged 3 different ways, since there's 3 different terms. And then remembering the even odd identities can help with simplifying. And these are considered the basic trigonometric identities that you need to just know like you know your name. So these identities should not merely be memorized, but should be known, just as you know your name, rather than have it memorized. So it needs to just be tip of your tongue. In a moment, you've got it. You don't have to think for a long time about it. So variations of these identities are helpful also. And so notice that if you have a 1 in the equation, you could replace it with sine squared theta plus cosine squared theta, which may help us with solving. It would seem like that would make it more complicated, but sometimes that's what's going to be what makes it so we can proceed. So what is the second equation solved for? It's solved for whatever's by itself on one side. So it's solved for sine squared of theta. And the third equation is solved for the cosine squared of theta. So get used to rearranging these, manipulating them so that you can use whichever form is the most helpful for what you're trying to accomplish. Okay, so objective 1 is to use algebra to simplify trig expressions. So some techniques that will be useful for working with trig identities, and these are the precursor to solving trig equations. We're trying to build your skills up so that you'll be good at solving equations when we get there. So some of the things you might do is multiply by a cleverly chosen version of the number 1, because you can always multiply by 1 and nothing changes, right? Because that's called the multiplicative identity. You might want to add a cleverly chosen version of 0, because you can always add 0. That's the additive identity. Making common denominators and combining numerators will often be a step that helps you make progress when you're trying to solve an identity. I find it helpful to rewrite all the trig functions in terms of sine theta and cosine theta. Sometimes I'll see relationships that I won't see until I do that. Factoring trig expressions is extremely important, so you need to remember all of your factoring techniques. So we're going to do a really brief review of those. So here's an example of a cleverly chosen 1, sine theta over sine theta. So I can multiply anything I want by sine theta over sine theta, and I won't be changing anything. I'll just be multiplying by 1, but it might make a sine theta appear somewhere where I need it. And then I could add cosine theta minus cosine theta. If I need a cosine theta to accomplish something, I can always add 0, and this is just a very fancy 0. So the factoring techniques you need to know. Factor out a GCF, and that should always be the first one that you look for, always, always. So factor out a GCF, then factor by grouping. And this is the only one we know that works with 4 terms. So you look for 4 terms and you say, oh, that's a factor by grouping problem. But first factor out any GCF if there is one. So then we learned factor a trinomial with a leading coefficient of 1. So remember, a trinomial has 3 terms, but now the terms are going to have trigonometric functions in them. Factor a trinomial with a leading coefficient not equal to 1. I use a slightly different technique for those. Difference of squares and the sum and difference of cubes. So these are all the factoring methods that you need to be very familiar with, and if you're not, then go back to chapter 1 and there's some good review in chapter 1. So everything you learn in algebra, you now need to bring to trig and use it to work with trigonometric expressions. So here's some helpful factoring tips. Recall the difference of squares factoring. If I have the cosine squared of theta minus 1, it factors as cosine of theta plus 1 times cosine of theta minus 1 because it's a difference of squares. But then also notice that because the Pythagorean identity tells us that sine squared of any angle plus the cosine squared of any angle is 1, that if I have cosine squared of theta minus 1, see how that gives me the opposite of sine squared of theta. So you have to really work at these. I don't know any other way to get good at them. So factor this expression is a difference of squares. So tan theta plus 1, tan theta minus 1. And then we have tan squared of theta plus tan theta minus 6. So you need to see this as term 1, term 2, and term 3. Terms are added or subtracted. And we have a tangent squared, so this is like a w squared. And then tangent is like w. So if it's helpful, you can switch to w's and say, oh, this looks like w squared plus w minus 6. Well, that I can factor because I remember how from algebra. And so I'm going to have plus 3 minus 2 in either order. And so then I can go back to, oh, but I had tangent theta, not w. So you don't have to do this substitution step, but if it helps you see the structure of what it is that you're trying to factor. Okay, so this next one has two things I would do. First, I would change anything that's not already sine and cosine to sine and cosine. So I would change cotangent to cosine theta over sine theta, and then that's times the sine squared of theta. Then cotangent of theta is cosine of theta over sine of theta, and that's times the cosine squared of theta. Well, now I'm seeing that there's a common term between these two, so there's a GCF of cotangent theta, and then if I factor that out, what's left is sine squared theta plus cosine squared theta that you need to recognize as a 1. So this equals cosine theta over sine theta, which is cotangent theta. So I didn't really need to go to sines and cosines, but I was just showing you that that's a technique that can be useful. Okay, so objective 2 is going to be establish identities. And if you've looked at the calendar, you'll see that I have allowed 2 full lesson days for working on this. It's so important. So here's some suggestions, but I can't give you a recipe for these. So that's why they're sometimes frustrating and challenging for students. But you'll feel your brain growing as you work on these and try something else and try something else and try something else. And if you don't see it today, try it again tomorrow and try it again the next day. And you will start seeing more things to try. So begin with the more complicated side as just a suggestion. It's usually easier to simplify a complicated expression than it is to make a simpler expression more complicated. And then you manipulate whichever side you choose until it looks exactly like the other side. So this is really, 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 really important. Do not manipulate both sides of an identity that you're trying to prove. This assumes that the equality is already true when that's what you're trying to prove. So it can be useful to do scratch work where you manipulate both sides so that you can see why they're equal. But when you're doing a proof, you choose one side or the other, you work on that side until it looks exactly like the other side. So we'll do lots of examples together, and we'll do these in class, and then I'm also going to have a worksheet for you to work on.